All right, everyone, let's take a look at your EMR unit test here. Question number 1. Which of the following sets of EMR, electromagnetic radiations, is arranged in order of increasing photon frequency? This is the way we want it to be asked, right? Because this is the way we remembered it. If you remember, we started off with, in the middle, visible light, which consists of red, orange, yellow, green, blue, indigo, and violet. Below red is infrared. Above violet is ultraviolet. And then, of course, we have radio waves and microwaves down here. We have X-rays and gamma rays up here. Since we're going in terms of increasing frequency, we're going this way, which means our answer has to be B, starting with radio waves and ending with gamma rays. Question number 2. Which of the following sentences describes the electric and magnetic field components of an EM wave? Well, 3 words that we memorized on that first day of this unit. We had accelerating charged particles. Accelerating charged particles are necessary to generate changing electric and changing magnetic fields. And the electric and magnetic fields need to be changing because they need to produce each other, right? A changing electric field produces a changing magnetic field, and a changing magnetic field produces a changing electric field, and so on. That's necessary in order to have EMR produced. And finally, those fields are perpendicular to each other and perpendicular to the direction of propagation of the wave, the direction of movement of the wave. So the answer to this question would be D. They are perpendicular to the direction of wave propagation. Numeric response number 1 says a skydiving team uses radio communication to remain in contact with each other and with people on the ground. If the radio sets operate on a frequency of 118 megahertz, we want to draw attention to this because we got to convert units. The wavelengths of the radio waves is what? Well, this one is pretty straightforward. We're just going to say V is equal to F times lambda. Lambda is equal to V over F. But V in this case is C, the speed of light, 3 times 10 to the 8 meters per second. So it's 3 times 10 to the 8 meters per second divided by the frequency. But be careful here. It's not 118. It's 118 times 10 to the 6 hertz. And if you forget that conversion factor, megahertz, or if you don't know it, then just check your data sheet, because in the middle of that data sheet it tells you all those metric prefixes like megahertz. Anyways, when we do the math there, that works out to be exactly 2.54 meters. No scientific notation here, just 2.54 that we bubble in. And question number 3. Atoms in a phosphorescent screen absorb energy of cathode ray particle. Whatever a cathode ray particle is, doesn't matter. You remember we've said this a million times. If there's something that you don't recognize in the question, it's not really relevant to the question. The important part here is that we have a photon with this energy, and we want to find the wavelength of that. And we have an equation on our data sheet in the top right-hand corner. It says E is equal to HF is equal to HC over lambda. We're going to use this part and this part. Let's rearrange that. The lambda goes up, the E goes down, and we get HC over E. Now, can we use joules here? Of course we can use joules. We always can. Can we use electron volts? We could. I'm not sure why we'd want to, because we've got joules given to us here. So since we've got the energy given to us in joules, let's just use joules all the way through the question. Planck's constant, 6.63 times 10 to the negative 34 joules seconds times 3 times 10 to the 8 meters per second, the speed of light, divided by E, the energy in joules, 4.11 times 10 to the negative 19 joules. You could have used electron volts here, right? You could have used 4.14, but if you did that, you would have had to convert the energy to joules, to electron volts. And again, I'm not sure why you'd want to do that in this case. That gives us an answer of 4.84 times 10 to the negative 7 meters. So that means the answer, of course, is B for that one. So we get some information in a box here. It talks about radio telescopes. Radio telescopes detect radio waves emitted by objects through the universe. They do not detect visible light. Talks about this antenna. And then it says in the bottom paragraph there, inside the information box, one of the radio waves that this telescope can detect has a frequency of 1,420 megahertz. Let's circle that again. And comes from the arm of the Milky Way. That is 7 times 10 to the 18 kilometers away. We don't know how much time in days. Watch that, because usually when we do this, we do it in seconds, right? This has got to be in days. That it takes the radio waves detected by the telescope to reach the Earth. So for this one, we're going to just say V is equal to d over t. Rearrange that to solve for t. T goes up, v goes down, d over v. The distance here is 7 times 10 to the 21 meters, because 7 times 10 to the 18 kilometers times 10 to the 3 is 10 to the 21, and divided by the speed of light is 3 times 10 to the 8 meters per second. We do that, we get an answer of 2.333 times 10 to the 13. So that looks like it's there, right? 2.3 times 10 to the 13. But it's not, because this is in seconds. To get that in days, we're going to have to first convert to minutes by dividing by 60. And then we're going to convert to hours by dividing by 60 again. And then we're going to convert to days by dividing by 24. So seconds to minutes, divide by 60 because there's 60 seconds in a minute. Minutes to hours, divide by 60 again because there's 60 minutes in an hour. And then divide by 24 to go from hours to days because there's 24 hours in a day. So the answer is not 2.3 times 10 to the 13. That would be seconds. The answer is 2.7 times 10 to the 8 when we do that math. 5. Dreo is located in a basin surrounded by mountains which shield it from man-made radio waves that interfere with astronomical signals. Man-made radio waves are produced by, well, we know that radio waves and microwaves are both produced by oscillating electric charge. So the answer for that one is C. The answer to your first question is, number 1 is Halifax. Write that down right now, because when you get to that question on this podcast that you have to answer, you're going to want to have it beside you rather than have to rewind. So number 1 is Halifax. Now we got a Michelson question. This is numeric response number 2. This is exactly what we expected to see. In fact, the diagram is exactly the same as you've seen a couple times before, except this distance is different. We're 29 kilometers here instead of some of the other distances we were given. We're looking for the frequency. It doesn't really matter what we're looking for here. We know we solve this the same way, no matter what we're looking for. We start off by writing down the equation V equals d over t. This t would be the time for 1/8 of rotation. Also corresponds to the time that it takes the light to go there and back. We also use this equation, t is equal to 1 over f. Big T is the time for 1 complete rotation. Now we're looking for the frequency of the rotation. That means we have to know the speed. We're going to use the accepted value, 3 times 10 to the 8, divided by the distance, which is not 29 or not even 58. Rather, it's going to be 58,000 meters, divided by the time for 1/8 of rotation. Solve for t1/8 there, gives us a value of 1.9333 times 10 to the negative 4 seconds. But that's not what we want. We know when we solve one of these problems, we always get a t, but it's never the one we want. We have to convert it to the other one. We're going to do that by multiplying by 8. Little t to big T, multiply by 8. That gives us 1.5467 times 10 to the negative 3 seconds. So let's sub that in. 1.5467 times 10 to the minus 3 equals 1 over f. Cross multiply there, and f gives me 6.47 times 10 to the 2 hertz. And I don't know if you remember this, but we said for frequency, we usually get 10 to the 2. Not always, but we usually get 10 to the 2 in the hundreds of hertz. So that seems like a reasonable answer. We're going to record that A, B, C, D, 6472. Next question is a refraction, Snell's law problem. A light ray is incident on a right-angled prism in air as shown below. The index of refraction of the prism shown above is what? Listen, there's some things here that don't matter. These angles don't matter. It doesn't even matter that it's a right-angled triangle. What matters is that we're going from air, which has an index of refraction of 1.00, to this prism, which has an unknown index of refraction. We're going to say theta 1 is the angle of incidence, 30 degrees, and theta 2 is 17.8 degrees. So let's just use Snell's law. There's two equations for Snell's law. N2 over N1 is equal to sine theta 1 over sine theta 2. And then we have N2 over N1 is equal to V1 over V2 equals lambda 1 over lambda 2. We're going to use the first one. Sorry, that's not sine theta 2. That should be sine theta 1 over sine theta 2. And we're going to we're going to rewrite. Actually, you know what? N1 is 1, right? So we're just going to say N2 over 1. That's nice because it just kind of disappears there. Is equal to sine theta 1, which is sine 30 degrees, over sine 17.8 degrees. So that just disappears. N2 is equal to sine 30 over sine 17.8. When we do the math there, it works out to be 1.64. That seems like a reasonable number, right? Glass was 1.5, I think. This is 1.64. We should know that C and D just can't be answers, right? C and D, because we can't have an index of refraction that's less than 1. The index of refraction of air and of a vacuum is 1. We can't be less than 1. Otherwise, the speed of light would have to be faster than 3 times 10 to the 8 meters per second in that medium, and that's not possible. Numerical class number 3. A physics 30 class performs an optics experiment with 4 different materials. The index of refraction of each of the materials is provided in brackets beside each material. The relative speed of light in each material ranked from slowest to fastest. Watch that, because you could get a question that says from fastest to slowest is what? Well, we know that light travels slowest in the highest index of refraction. Remember, as n goes up, v goes down. So we're looking for the one with the highest index of refraction. That means ruby is going to have the slowest speed, and then glycerin is going to be next, and then water is going to be next, and then ice is going to be next. So we're going from highest to lowest index of refraction. Now we got some binoculars here that involve some refraction. It describes how it works here. And it also says it uses total internal reflection to reroute the light. So we've got total internal reflection happening right here, right here, right here, right here. And then it goes out the lens at the end and magnifies it. We want to find the critical angle between a prism-air interface. Now, we're not told whether it's prism to air or air to prism, but we know to get total internal reflection, we have to go from high index to low index. So we're going to say the prism here must be medium 1, and the air must be medium 2, high to low index of refraction here. So let's say N2 over N1 is equal to sine theta 1 over sine theta 2. N2 has a value of 1.00, and N1 has a value of 1.50. Remember, we're going from prism to air. So prism is 1.50, air is 1.00, equals sine theta c, the critical angle, over sine 90. That just disappears because sine 90 is 1, of course. So we're going to say theta c here is equal to the inverse sine of 1 over 1.5. And when we do that, that gives us an angle of 41.8 degrees. And that seems reasonable as well. No scientific notation here again. We just sub it in. Don't forget the decimal point, though. 41.8. The answer to question number 2 in your little quiz to see if you're following along with this is social 30. So write that down as well. And when you get to that question in the podcast, click on social 30. Question number 7. In a photoelectric effect experiment, a student observes how changing the intensity of radiation, intensity, remember, a synonym for intensity. If you take out your little imaginary physics thesaurus, intensity means number of photons. So we're looking at how changing the number of photons affects the current here. And again, if you take out your little physics, imaginary physics thesaurus, the current would be analogous to the number of electrons, or proportional, I should say, to the number of electrons. We know that more photons causes more electrons. More photons causes more electrons if we're above the threshold frequency. And in this case, it says pretty clearly here, if you read carefully, we're below the threshold frequency. If we're below the threshold frequency, of course, you know what happens. Nothing happens. And if nothing happens, the intensity isn't going to affect the number of electrons at all. More photons, so what? Remember, you got one piece of paper, causes nothing. 100 pieces of paper causes nothing. 1 photon, nothing. 100 photons causes nothing. So the answer for this one is D. Doesn't matter what the intensity is, the current or the number of electrons ejected isn't going to change. Numeric response number 5. We get a diffraction grating with openings that are 5 times 10 to the negative 5 meters apart. That's going to be little d. We have a wavelength of 665 nanometers, which we want to convert to meters. 665 times 10 to the minus 9 meters. And it says the angle between the central max and the third order minimum. Careful here. Central max, first maximum, second maximum, third maximum. The angle between the central maximum and the 1, 2, third order minimum. That angle is what we're looking for, but the value of n there, and watch this, is going to be 2.5, not 3. Third order minimum is between the second order minimum and the second order maximum and third order maximum, so n would be 2.5. We're going to say lambda is equal to d sine theta over n, and we're going to rearrange that. Sine theta is equal to lambda n over d, and theta is therefore equal to the inverse sine of lambda n over d. So sub in all those numbers here as we have them written down in the Givens, and we end up with an angle of 1.91 degrees, which is small, very small. But that's our answer. Multiple choice number 8, tricky question here, I thought. This is one of those relationships again. It says, if the students switch from using a red laser to blue laser, remember what we're doing here. When we're going from red laser to blue laser, we are increasing the frequency. If we're increasing the frequency, we're decreasing the wavelength. So let's look at that. We're decreasing the wavelength. What's going to happen to the distance between the maxima? Remember what we said, whenever you have a question where you're trying to find a relationship between two variables, write down an equation. The easiest equation to deal with here is lambda is equal to xd over n times L. We want to find how changing lambda affects the distance between the maxima. In other words, x. So let's solve for x. X is equal to lambda times n times L over d. Now, if we're decreasing lambda, then x will decrease as well because they're directly proportional to each other. That means the answer has to be either C or D. Lambda goes down, x goes down, the distance between the maxima goes down. Now, the next part of it, this is the tricky part, I thought. In order to make the spacing between the blue maxima, the same as it was originally for the red maxima. So in other words, we want x to go back up. What do we have to do to the distance between the slits? So now let's rearrange this to solve for the distance between the slits, d. I get lambda n L over x. I want x to go back up. X has to go back up because when we switched from red to blue, x went down. And now we wanted to go back to what it was originally for red, so x has to go back up. In order to make x go up, we need to make d, the distance between the slits, go down. Like these are inversely proportional to each other. So as d goes up, as x goes up, then d has to go down. So we're going to find that has to be decreased as well. The answer is D. Number 6, pretty straightforward photoelectric effect question here. The work function of a surface that is a threshold wavelength of 7.1 times 10 to the negative 7 meters is what? We're just going to say W is equal to HC over lambda max. We're going to rearrange that. Lambda max is equal to HC over the work function. Just cross multiplying there, right? Now, we're looking for the answer in joules. You could do it in electron volts if you wanted to, but since you're looking for the answer in joules, it makes sense just stick with joules throughout the whole question, right? So let's do that. Let's say lambda max is equal to 6.63 times 10 to the negative 34 times 3 times 10 to the 8 divided by the work function, which is 7.1 times 10 to the negative 7 meters. We do the math on that one, and that works out to be 2.8 times 10 to the negative 19 joules. And we're going to express that ABCD is 2819. 2819. Answer to question number 3 in your little quiz to see if you're paying attention, following along, is red. So write that one down so that you don't miss it. Number 3 is red. Question number 9, the last page of our multiple choice booklet here, the last question, in fact, of our multiple choice booklet, says phenomena demonstrated by EMR. We want to know basically which of these phenomena show the wave theory of EMR versus the particle theory of EMR. Now be careful because these are backwards, right? Usually we see wave first and particle second. If you remember, on the very first day of this unit, we talked about 4 properties of EMR that are exhibited by waves. We said diffraction, interference, refraction, and polarization. Diffraction and interference would both be waves. And then we said near the end of the unit, there were 2 things that we learned that demonstrated the particle nature of EMR. One was the photoelectric effect we did first, and on the last day of this unit, we talked about Compton scattering. So that would be the particle theory of EMR. So the particle model would be 3 and 4, and the wave theory would be 1 and 2. So the answer for that one is D. Now we're going to take a look at our written response. What do we have here? The 4 questions on the written response booklet. Starting with number 1. A 4 centimeter tall upright object is placed 10 centimeters in front of a converging mirror. First thing we do here is circle this, right? If it's converging, we know the focal point is positive 8 in this case. We want to calculate the image distance, and then we want to identify 2 of the 3 attributes. Of course, we know there are 3, and I would accept any 2 of the 3 possible attributes of this. Let's write down some givens and go from there. The object height is 4.00 centimeters. It's upright, so it's positive. The object distance is 10 centimeters. It's always positive for us. The focal length is positive 8.00 centimeters. And it's positive because we said it's a converging mirror. We're going to solve for DI here. So I'm going to say 1 over F is equal to 1 over DO plus 1 over DI. 1 over 8 is equal to 1 over 10 plus 1 over DI. And we're going to do our little trick on our calculator to solve for this. We're going to say 8 x to the minus 1 subtract 10 x to the minus 1. So 1 over 8 minus 1 over 10. And then we're going to flip it over. And we get, I'm in scientific notation here. I don't want to be. So let's go back to, let's try that again. 1 over 8 minus 1 over 10. Now let's flip that over and we get 40. So DI is positive 40 centimeters. There's your first point out of 2. And then what about the attributes? Well, because that's a positive DI, that means the image is real. Now, in order to get the other attributes, we would have to find something like the magnification. Negative 40 divided by DO is 10. So the magnification is negative 4. You weren't asked to solve for the magnification here, but to get the attributes, unless you used a ray diagram or a pattern, then you would have to do this. The fact that we get a negative value of magnification tells me that the image is inverted. And the fact that we have a magnification that's 4 tells me that the image is larger. So it's larger, inverted, real. Any 2 of those 3 works for us. Number 2, a 9 centimeter tall upright object is placed 10 centimeters in front of a diverging lens. Diverging lens, that tells me the focal length is negative. Watch that, right? We always circle that so that we don't forget those negatives and positives. What's the image height? Identify 2 of the 3 attributes once again. So we're going to say HO is 9.00 centimeters. DO is 10 centimeters, 10.0 centimeters. F is negative 3.00 centimeters because it's diverging, and we're looking for HI. Now, in order to get HI, we first have to find DI. We're going to find that by saying 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 3.00 equals 1 over 10 plus 1 over DI. We're going to solve for this pretty much the same way as we did the last one. Let's say negative 3, x to the minus 1. Now let's subtract from that 1 over 10. And then let's flip that over. We get a value of DI of negative 2.3077. Now, that tells us right now, even though we weren't looking to solve for DI, that tells us right now that we have a virtual image. Remember, when we have F, DO, and DI, positive means real, negative means virtual. So a negative DI means a virtual image. Now let's find the image height. I'm going to say HI over HO equals negative DI over DO. Let's say HI over 9.00 equals negative, because DI was negative 2.3, negative 2.3077 over 10. Divide those two numbers on the right, multiply it by 9, and solve for HI gives me positive 2.08 centimeters. So there's 1 point. And then the fact that it's positive tells me that it's upright. And look, we're already given the height of the object is 9, and the height of the image is 2. So clearly it's going to be smaller. 2 as opposed to 9. Almost there. Look at that, 27 minutes and we're almost there. The answer to your fourth question is September. Write that one down so that you can answer it in a couple minutes when you see that question pop up on the podcast. September. Here's a little fill in the blank here, eh? It's like elementary school, fill in the blank. Statements about the photoelectric effect. Nothing happens. More photons are ejected. Higher energy photons are ejected. More electrons are ejected. Higher energy electrons are ejected. Listen, guys, a fairly common mistake throughout this was 3. That's not giving me the answer for any of these. Higher energy photons are ejected. Photons are not ejected in the photoelectric effect, period. Electrons are ejected in the photoelectric effect. So 3 won't be the case. 2 won't be the case as well, actually. So we can eliminate 2 and 3 as being possibilities for any of these. Either nothing happens, or more electrons are ejected, or higher energy electrons are ejected. In no situation with the photoelectric effect will photons be ejected. All right, question number 1. It says if we shine light on a metal, but the light is below the threshold frequency, well, of course, nothing happens if light is below the threshold frequency. If we shine light on a metal and the light is above the threshold frequency, but we make the frequency even higher, now we're increasing the energy of the photon, right? Higher energy of photon, higher energy of the electron. The answer is going to be 5 for this one. Be careful because, like I say, a number of people actually put 3 for this one. Higher energy photons were rejected. But I don't think it was because people didn't know the difference. I think it's because they didn't read carefully. Watch that. See, if we shine more light, of course, means more photons. More photons, but the light is below the threshold frequency. It doesn't make any difference. Below the threshold frequency, no electrons will be ejected, no matter what. D, if we shine more light, more photons, but the threshold frequency is above the threshold frequency, what's going to happen? More photons. While we're above the threshold frequency, we're going to get more electrons ejected. If we increase the frequency slightly, but keep it below the threshold frequency, so we're increasing the frequency, but we're still below the threshold frequency, then nothing is going to happen ever. And finally, If we shine light for a longer period of time, that's more photons. More photons means more electrons ejected. So the answer for that one is 5. And finally, our last question here. Calculate the maximum speed of a photoelectron emitter from a metal whose work function is 1.5 eV. When the metal is illuminated with light of frequency 2.5 times 10 to the 15. Because we're looking for speed, and we're going to have to use 1/2 mv squared, I want to convert that 1.5 eV to joules. Remember, you can use electron volts usually, but as soon as you introduce 1/2 mv squared or QV stop, then you've got to use joules. So let's do that right off the top. Let's say 1 EV is 1.6 times 10 to the minus 19 joules, which is 1.5 EV to X joules. Cross multiply, X goes up, 1.9 goes up. We end up getting a value for X of 2.4 times 10 to the negative 19 joules. So we're going to say work function is 2.4 times 10 to the negative 19 joules. We're going to say the frequency of the photon is 2.50 times 10 to the 15 hertz. And we're looking for the speed. So I'm going to say, probably haven't come up with anything in the first 5 seconds. So I'm going to use my 5-second equation. HF is equal to EK plus W. I'm going to use joules here. 6.63 times 10 to the negative 34 has a frequency of 2.5 times 10 to the 15. I'm going to use joules because I'm going to introduce the 1/2 mv squared into here, right? The 1/2 times the mass times v squared, because that's what we're looking for is v, plus the work function in joules, 2.4 times 10 to the negative 19 joules. So get this number on the left-hand side. I don't have it written down, so I'm not exactly sure what it is. Get that number on the left-hand side. Take that over by subtracting. So that gives you a number on the left-hand side equals 1/2 of 9.11 times 10 to the minus 31 times v squared. So what I would do at this point probably is calculate half of 9.11. That gives me 4.555, I believe, times 10 to the minus 31. And then we'll take that over by dividing. And then we'll square root to get speed. And guess what we get? 1.76 times 10 to the 6 meters per second, which is exactly in that range that we expect to get, right? 10 to the 6 meters per second for the speed of a charged particle. So I'm pretty comfortable with that answer. All right, that's it. 5 bonus points for submitting your corrections to the test and for completing watching this video. So you're halfway there now, maybe all the way there now if you've already done your corrections. All right, that's it, guys.